Plugging in the
third A. Yeah, this one.
Yeah, we need to find a way to do it.
So let's see. Well, I like it. Let's see. Squares go away. I love it. So that limit is dependent on M.
I think that works.
What's happening here? Oh, you just tried some. Okay. Oh, I see. But here the limit would be 1, right? But here it depends on what M is.
Yeah.
So there you go. So therefore the limit does not exist because if you choose a different slope, the limit's going to be different along that path.
Yeah.
Perfect. So you just did this effectively in 3 dimensions. They don't agree.
I don't think it's very rigorous, though.
Why not?
Like, because you're just hoping and praying that
No.
some poly, like...
But your definition of rigorous is incorrect. That is a counterexample. So for a counterexample, I just need to find one situation where it doesn't do what it's supposed to do, I'm done. So if the limit did exist, then every path has to agree. You found an infinite number of paths that don't agree.
But what I'm saying is, like, I could pick 6 different functions and they all agree. That doesn't rule out the possibility.
I never said now. So why do you do the path thing? Because you hope that 2 of them don't agree at least, right? If they all seem to agree, what do you then have to do? You have to do something else. Squeeze theorem or even epsilon delta. You then have to use some theorem because specific examples can never prove something, obviously, right? But they can certainly disprove something. So first you try to disprove it, and then you go, oh shit, I keep getting this, so I better use a theorem that will actually prove it no matter what. And of course, the theorems you would use are themselves rigorous. So counterexamples, the idea of rigor, you just need 2 that don't agree. So if you find 2 that don't agree, you're done. There's no way the limit could exist.
Why not go straight to the theorem?
Because the theorem is going to show you that the limit is this. Well, the first thing you want to try to do is show that the limit doesn't exist, because that's the easier thing to do. And I don't know how many of you guys did the epsilon delta stuff back in Calc 1. I'm one of the few that does it for my students, because I try to get you ready for your future. I don't know, I just think that's a good idea. If you did the epsilon delta proof, to use it, you have to go into it having a good idea what the limit is, right? So if I do several paths and they keep coming up with the number 3, they keep agreeing at 3, all these different paths I use, then I could use the epsilon delta proof and put a 3 in there as the limit. Now if I do the proof and it doesn't work out, then I go, okay, I got to go back. There's probably a path that doesn't work. I just haven't found it yet. Right? So I am not saying that you can prove a limit through specific examples. That's impossible. But you can disprove it with specific examples all day. Okay. Let's do these. The first couple should be very simple. So like part A is, please let that be easy. Right, I mean, what do you do? Don't make me write a lot. Yeah, plug them in. So if x is 1 and y is 0, you're left with 5 plus 1. So you get 6, and you all make every single one like that. So, part B, again, you gotta first check. Don't just assume that and you start to try to factor and stuff. When you plug a 0, 0 in, you get 0 over negative 3, which is 0. Okay, I like it. And then now part C is the one you got to do a little bit of something. Yeah, exactly. So the top you can take a 3 out, and then you can factor that. And now you can plug in a 3 and a 1. And you get 3 plus 3 is 6 times 3. 18. Cool. Okay. And then a little bit further down the page are the ones about the paths you take. So what path did somebody choose? What's one path somebody chose here?
1 minus m, 1 plus m.
Christian, you're going to make me go to sleep, man.
Sorry.
It's all right. So I'm sorry, do it again, Christian.
1 minus m and 1 plus m.
Oh, okay. 1 minus m is
So
what?
if y equals mx.
All right, I got you. I like it. Now, real quick, there's nothing wrong with that. But what was my suggestion earlier? What if you use the path x equals 0? What do you get? No, you don't.
-1.
You get -1. You see that? X equals 0 leads to a limit of -1. And y equals 0 would lead to a limit of what? 1. Oh, done. 2 paths. There's a reason I said that suggestion, because it actually is a great thing to try first, because you can just look at it, bam, bam, you know, and if it comes out to be the same number, like, oh shit, maybe I do have to do mx. Nothing wrong with doing mx, by the way, nothing wrong at all, but be nice to yourself and eliminate the conditions that make it easiest and quickest to do, right? Now, if you use mx, I don't know if anybody else did mx.
Can we use y equals 2x if we want?
Hell yeah. As long as you have something else to contrast it to. What other path did you do?
Y equals 0.
Kick ass. I love it. Christian's line, I just want to do every line. Right? Sounds terrible. You can take that one. Christian, come on, share, man. So, oh god, did I just make a quick change? There's one class that I was saying is something about, somebody was talking about they like the art better than math. I'm like, well, you know, some people like corn and some other, and they're like, are you saying corn? It's like, no, I am not talking about people enjoying that. I love it. So what does this become? If I let y equal mx, this will be m squared x squared. So then you can kill the x squares. So you get 1 minus m squared over 1 plus m squared. And there you go. You have a limit. And that's what the limit equals, is that, because it's not dependent on x anymore. It's like, well, I don't know why I still have an xy in there, but too bad for me. That's that, and so it depends on m. So it depends on the slope of the path you pick. So you pick the slope, a flat slope and a 2x slope, and it comes out to 2 different things. Christian just picked every single possible one, and it depends on m, so therefore the limit does not exist, because it would be different for every line you chose.
What if I do y equals mx and then external its number?
Oh, sure, yeah. If the m's cancel and you come out with a number, then you all you know is that every linear path agrees. But so maybe a parabolic path would not agree. That's where you might want to start thinking about doing a theorem. Maybe that is actually the right, because it's very difficult for this doesn't never happen. So this sometimes happens. There you go. Where every single possible straight line agrees, but some other path doesn't. But if you do y equal mx and or mx plus b if you need to, and it comes out to a number, then I feel pretty strongly that could very well be the limit. I'm not saying it will be, but it could very easily be. What about this next one here? Did anybody else do something different there?
X equals a square root of x.
What'd you do?
A square root of x. Y equals a square root.
Y equals a square root of x. Ooh, I like that. Mike is like, I don't like all that freaking square shit. Let me knock that down. So then, as x goes to 0, y goes to 0. So I'm going to go to 0, 0 like I'm supposed to. So you would get x squared minus a squared x. right? Over x squared plus a squared x. And then where'd you go from there?
Well, I factored out the x's.
Good.
They canceled, and then when you plug in zeros, you're
So you get x minus a squared over x plus a squared.
Yeah.
So when you plug in 0, you get,
Element x.
well, what do you get?
Well, you would get negative.
So that's not,
But it contradicted with one of my previous.
oh, there you go. So you use 2 paths, I got you.
Yeah.
One path you chose is this one, and then you used a different path and got a different number. Kick-ass. Yes, sir.
Can we see this one like on Wolfram Alpha or something? Because all the linear paths do agree on this one, on 0, but then the parabolic path of that one don't. So I'm just curious to see what that looks like.
Oh, this here. Now wait a minute. You're not talking about this one here, are you?
No, it's that one.
No, that's the same one. I'm sorry.
It's the other one.
This is using this.
Oh,
Yeah.
Oh, okay.
Cool. Yeah.
Sorry.
Ben, I agree. There are remarkably funky functions that have that happen.
The next one.
The next one. Let's see what happens in the next one here. All right. So what paths did you guys use?
ax squared. Y equals ax squared.
All right. Yeah, we'll flip it up a little bit. We'll use.
And then y equals x squared.
Do the other one as y equals mx.
We did y equals x squared and y equals ax squared.
So you did the same thing twice. You
But
understand?
you end up with 2 different.
If a is 1, so if your limit is dependent on a, you're done. You only need 1 because you just did a lot of paths at once. How many paths am I doing if I do this? Infinite number. Not all of them, all the parabolic paths, right? An infinite number of them, right? So I'm coming in like this, or I'm coming in fat. My a is tiny. I'm coming in fat. Or I'm coming in hot. You know, coming in really tight to it. Yes.
Could, when you do, like, if you were to do all powers of x, could you go y equals x to the n?
Yes. Did you try that?
I didn't, but
Oh.
could you?
I mean, it gets a little strange sometimes. But when you have polynomial, when you have rational functions, a lot of x's might cancel for you, right? You just have to be, all you need are 2 paths, so you can eliminate any path that has problems, because that's what that might lead to. Radical paths are problematic, because you might have elements in your domain that would make those unreal, right? Anyway, so yes, you could. It just sometimes gets a little overly freaky. Wait a minute, okay, so what do you get when you do this? As x goes to 0, y goes to 0, so I can just replace y with all these and let x go to 0. Is everybody cool with that transition there? I'm like condensing all my variables to 1 by imposing this restriction. So then this would become 2ax to the 4th over x to the 4th plus a squared x to the 4th. I like it. So all those x to the 4ths go away, and I'm left with this. That's the limit, right? Because the x's went away, so that's just a constant according to the limit, but we know it's not truly a constant, because when a changes, then I get different answers. So you were done after that, to be honest. I really want to make sure you understand the difference between that is multiple paths in its own right. My answer was dependent on this. So there's at least 2 paths. I mean, there's an infinite number of paths. Pick an A. But if you get, if the path you choose doesn't have a variable part of it, and what do I mean by that? I don't mean x and y, I mean this. That makes it a family of paths. Do you know the word family? You know the family of functions? When you do the plus c shit, you make it a family of functions that answers. So when you do a family of functions, then as long as your limit answer is dependent on that parameter piece of it, then you're done. because it's going to be different as that changes. If it comes out to a constant, you need another path. I like it. So like what happened to you earlier, I think.
Yeah.
Right? Okay. Oh, so I'm done. Okay. Is that cool? Anybody else try? I'm sure somebody else tried something else, right? Did somebody try MX?
I did MX first and it came out 0.
Yeah, so when you do, if you do MX, you get x goes to 0 of 2mx cubed over x to the 4th plus m squared x squared. So you get 2mx over x squared plus m squared. Is that right? Does that look good?
Yeah.
You can kill 2 x's, right? And then if you let x equal 0, you just get 0. And then, see, that's where it kind of sucks. You have an entire family. All the linear functions agree. I like it. Oh, so this is the one. I like it. All the linear functions agree on the limit, but then you got the parabolic functions don't. So this one is definitely would be a nice one to look at in Wolfram Alpha for sure.
Can I get it?
Do you have access to Wolfram Alpha?
Not really.
I just don't want to wake this computer up. Might yell at me. Well, let me see. I'll get him started. We'll get into something else here. All right. So how do you guys feel about this idea of path? You have to be kind of familiar with the idea of path to even know what to try. I like it. I just want to do a little bit. Let me see if I missed anybody. No. Okay. I like it.
Are there some catch-all functions that we throw in, like we tried the linear, y to the plus b, and then we tried the parabolic, and if they all agree, okay, they're all going to 1, and all the parabolics are going to
Then that means you have to go do something else to prove it. So, like was said up here, John had a good point. You can't stop there and say, well, the limit's this. Because look at all these things. Because here, we did an infinite number of paths, and they said 0, but it turns out that that's not the limit, right? So you could do 1 billion paths, and all of them say the limit is 2. But there's one little path you didn't even think to even try, and it says, the limit's 1, I disagree. You know. So the theorems will flesh that out.
Are there any like catch-alls that we can throw in our homework? Like we should try this.
That is the greatest question if there was an answer to it, but there is none. Yeah, there's no catch-alls. There can't be, because it depends on the function in its particular whatever it's doing. Yes?
So would it be the limit of plus is 0?
What's happening? What's up?
Because if we divide the denominator and the numerator with a, so we get
Well, no, you'll just get.
divided.
Well, you'll get 2 over 1 over a plus a.
Divided both with a squared.
But no. It doesn't matter, because what's a doing? Nothing. A is a number. A is any number you want it to be. So a is not 0,
But
right?
if we use 0, we'll get to 0.
No, it won't.
There's an example right here, and it's
Well, now look at the difference here, though. Is that the same exact thing as this? What's different? The bottom is not as symmetric. It's not. The bottom here has got the same degrees, right, on the x and the y. So that's that. That's the. Let me see. Blah blah blah. Let's see. Did I use the right example? I think I did.
Your x's are different powers.
Let me double check this. I think I. Well, let's see. Let's see. I might have chosen the wrong function to use as an example down here. No, yeah. Let's check it out. If I do, let's do this real quick. Let's do a couple of paths for this one. This is the one that's at the bottom of the page. If I use y equals mx, I end up with, let's see, mx cubed over x squared plus m squared x squared, right? So then the limit as x goes to 0 would be mx over, I think that's what saves this. I'll gather x squared. So then as x goes to 0, this goes to 0. Alright, now that's not good enough for proof. In fact, what I'm doing right now is not good enough for proof. But then let's try, what was the one we just used?
Ax squared.
Ax squared. So then we would get, I'm just going to not write the limit. Is that cool? You guys should. Alright, so this will be ax to the fourth, right? Over x squared plus a squared x to the fourth. So then you can kill, yeah, it's because of those powers agreeing on the bottom. I can kill a couple of x's, right? But then if x is 0, it's still 0, because the 1 saves it. So that's what saves the ass of that one is. The powers on the bottom were the same. The degrees were the same. So it's that slight, do you guys see the difference between the one we just did, where the limit didn't exist, and the one that's down on the bottom of the paper? It's got a difference in the power. So it's that slight difference that would suddenly make it work or not work. That's all it really took. Now, I'm not saying I just proved it. I proved it with the squeeze theorem. And Ben has a good point. The whole thing should be in absolute values in the middle there. So it should really look like this here on this step. Where'd it go? There it is. Yeah, I just forgot the absolute values in the middle. But if you've seen squeeze theorem before, this should feel familiar. And the book kind of goes straight to epsilon delta, which is kind of dumb. I don't know why, because it actually uses squeeze theorem in the solutions manual. It just uses squeeze theorem. Like, that's kind of evil. So squeeze theorem can be used on the ones that you think have a limit at 0. So you can do squeeze theorem in the book. So the way you attack these problems is you pick a few paths, you hope to God, try y equals 0, x equals 0 first. And then maybe try y equals mx, try y equals x squared. If you keep getting the same numbers, then you might want to take a step back and think about squeeze theorem or something else that will be the proof of it. And do you guys remember squeeze theorem? The reason it's called squeeze theorem is if I have a function f and I have a function, Jeff, you're going to do different colors because you got all these colors. I got pink. All right. I got a function g. Oh, pink is so weak. And I got in between there, I got some function h that's always in between f and g. And if f goes to some limit at a and g goes to some limit at a, then h has to go to that the same limit. That's why it's called the squeeze theorem. It's like there's no options for it. I got choices. I got no choice. Shit. All right, so that's why it's got the name. So it's the same kind of exact same idea in 3-dimension in multivariable functions.
So what you're saying for this example here is still doesn't exist. If we should like that.
Why is that?
The one you said the example.
Say again, sir.
With this example, if you choose another path, it still doesn't exist, not to 0.
Why doesn't it exist? No. That's different problems. Here's the one that's on the bottom.
Yeah.
And I got 0 this way, I got 0 this way.
So you say the use of squeeze theorem is not 100% correct?
No. This is correct.
But if we choose another path for this, then it will not come to 0. Like for example, y will be 2x squared.
Oh, I chose that path.
Yes.
I did already.
Okay.
If you let a equal 2, so, all right. All right. You ready? So y is 2x squared. What'd you get for the what's it look like when you plug that in? Y equal 2x squared. It'll be 2x cubed on the top, right? So you'd use the path y equal 2x squared?
Is it 2x to the square?
No. All right, what path did you use?
Y equal to ax squared.
Oh, y equal to ax squared. All right, so that's what I did here.
Yes.
So do you disagree with what happened here?
No, I don't.
Okay, and then if you let x go to 0, what do you get? 0 over 1. Right? Do you see right here? Are you cool with this? Are you cool with this one right here? So then you can divide everything by x squared. So you still have a 1 here on the bottom. See that? That's what saves its ass. So when you let x be 0, you get 0 over 1 plus 0, which is still 0. Which again is not a proof. This is a proof. That, no proof. Not a proof. I like it. Okay. So just a couple things about partial derivatives. This is section 14.3. So even if you've never been to this point, I was talking about this the other day. Partial derivatives are specifically along the x and y axis. So like we said yesterday, I introduced the idea of something else called directional derivatives, which could be along any direction I want to relative to the x and y. So when I say the partial derivative with respect to x, that would be as x changes. If you say the partial derivative with respect to y, that would be as y changes.
Could you have a partial derivative in respect, like where y equals x squared?
Along any curve, you could. Would it be a good thing to look at? Would it be a nice, pretty thing? Not necessarily. Yeah, but so you could do the integral along any curve. You could actually do. All right, you got me going here now. So you got like we always have this. We always have this covering over the xy plane. Is that cool? So the outputs all make this covering. There would be like a volume underneath that, right? All right, but what I could do even is go along a line and say, what's the area between that line and the covering? So I can do what's called a line integral. As I do some little meandering thing, I can see, well, how much area am I picking up as I move through this? Because what this could be representing physically is a magnetic field. It could be representing a flow of something. So I'm talking about how much stuff am I picking up as I move along this path. Right? So you could do that to figure out what's the best path to go through so you don't pick up too much shit if it's going to hurt I got a spaceship in mind or submarine or something. Do you guys kind of get that's in our future. So there's a lot of stuff you can do along any curve that you can imagine. I like it. We're not there. We're definitely, let's take a giant step back. All right. So remember the other day, I was talking about that one place as you're going towards the airport, there's that Laurel. If you've never been there, you can imagine. You've got stopped at the stop sign, and immediately the ground just goes, wah! Right? And crazy people try to cross there. And if I look this way, so as I look along the y-axis, my z changes quickly this way, right? As I look along the x-axis, it's straight. So my partial with respect to the the y direction, as I'm looking this way, would be negative. As I look this way, it would be 0, because it's flat that way. Do you guys, the concept. Now thank God. So what's happening? If I'm saying as I move this way, what am I keeping constant? I am not moving I'm only moving in what direction? The y direction. So I'm holding x Constant. No, constant. I like it. And if I'm going this way, I'm holding y constant. So thank God the computation is exactly that. So if I had a function, say x squared y. The notation we use gets kind of nifty. So I'm going to show you the couple different ways to do this. This would represent the derivative of that function with respect to x. So what am I holding constant? Y. I'm holding y constant. Yes, sir?
With respect to z, holding x constant. Right?
No, this is with respect to x. It's how z is changing. So another way to write this same thing is, all right, let me do this step by step here. I'm going to show you several different ways to write the same thing. So it's partial derivative. So I can't write a full d. I write a partial d. Or a little d. So that's the partial derivative symbol. Let that sink in. Different teachers do it differently because they write better than me. But that's what mine looks like. It don't look like a d, but it looks like a d enough for me to know that's a derivative, but it's a partial derivative. All right, so this would be a nice, complete derivative. This is